So here's our little diagram, and it says one leg is 3 centimeters and one leg is 4. So 3 centimeters and 4 centimeters. And I hope you appreciate how nice I am, because that means the hypotenuse is 5. And the question wants to know what's the net force on the 3 microcoulomb charge. So the 5 microcoulomb charge is going to put a force on the 3, and the negative 3 microcoulomb charge, no, negative 2, sorry, it's a 2. Negative 2 microcoulomb charge is going to put a force on the 3. So first we have to find those two. So if we call this one number 1, this one number 2, and this one number 3, then FQ13 is going to equal KQ1Q3 over R squared. So 9 times 10 to the 9th Newton meter squared per coulomb squared over 5 to the negative 6 coulombs and 3 to the negative 6 coulombs. And remember, you have to change your centimeters, so 0.04 meters squared. So type that in your calculator, and when you do, you should get a force of 84.375 newtons, I believe. Okay? And so now you're going to do FQ23, and feel free to stop the video and do this one on your own, and then turn it back on to so that you can catch up to me. Okay? So if you stopped it and then turned it back on, here I am doing what you just did. So 9 times 10 to the 9th Newton meter squared per coulomb squared. One charge is negative 2 to the negative 6 coulombs, and the other is positive 3 to the negative 6 coulombs. And the distance between them is the 3 centimeters, so 0.03 meters squared. And when you do this, you should get a 2,3 of negative 60 newtons. Okay? So it's not in a straight line anymore. So it's not, you can no longer just, add or subtract. You have to look at charge number 3. And remember, this negative means it's an attracting force, whereas the positive means repelling. So what is number 1 doing to number 3? They're both positive, it's repelling, so it's pushing it down. What's number 2 doing to number 3? It's attracting it. It's pulling it over. So this is your 60 newtons, and once you draw the arrow, drop the negative. The negative's just telling us it's attracting. And this one is the 84.3, etc. What was it? 375. Okay, so they're at right angles. So slide 1 over, and then your hypotenuse will be your resultant. So this will be the force on charge number 3. Square them, add them together, take the square root, and when you do, you should get 103.533 newtons. Okay, and now find the angle right in here. So it'll be 84.375 divided by 60. Take the inverse tan. So it's going to be bigger than 45. So I think you get 54.583 degrees. And then which way? Well, that's clockwise, and this is positive x. So CW positive x. Okay? So some of your homework tonight is going to be with guys like this. Unfortunately, in the textbook, they're a little mean, and they also make you find it on the corner ones. The one at the base at the right angle, it's easy because they're already perpendicular to each other. But if we did the net force, just reaching for a different pen here, if we did the net force on like number 1, number 3 would be pulling number 1, or pushing number 1 away. So this would be FQ13. And then number 2 would be going at an angle. It'd be pushing number 1 up like this. So this would be FQ12. So once you find them, then you would have to break this guy up into its x and y components. So this would be the x component, this would be the y component, except I just lied, 2 is negative, it would be pulling it down. This would be the x, sorry about that, this would be the FQ12x, this would be the FQ12y, and once you found them, then you would subtract the y's to get the total in the y, the x would just be the x, and then you would redraw your new triangle and find the resultant, and this would be the FQ11. Okay, so it'll be a little bit more challenging than when they're at the corners. So 3 of the questions I would like you to do for Thursday are on page 640. Page 640, and they're numbers 6, 7, and 9. 6, 7, and 9. So I'm skipping 8 and 10 because I'm a nice person. Is it bad that I have to point that out? And just for a second about 6. 6 says you have a proton resting on the surface, and you take a second proton and you place it above it, and it wants to know, where do you have to put it above it so this guy will just float here? So again, it's some of the forces. You just have to think for a second, what are the forces acting on this guy? Well, there's always our good friend, good buddy, gravity acting down. And because these are positively charged, there's going to be a force of repulsion acting up, which will be FQ. So if it's hanging out here like the question suggests, it'll be FQ is equal to FG, which means KQQ over R squared has to equal mg. Okay, and then you can solve. I think it asks you to solve for R maybe. Okay, but really it's just doing the sum of the forces on it. So that's for number 6. Okay, so 6, 7, and 9 for Thursday. The one other new piece that I wanted to talk to you about for the last couple of minutes of this video is electric field. And there's a new sheet of notes that you can pause this video while the teacher gives out the new sheet of notes. It's electric field, and it's a capital E. We talked about electric fields the other day when we talked about gravitational fields. Remember, gravitational field was little g, and it was equal to either Fg over m, or it's equal to Gm over R squared, where this m is the mass brought into the field, and this m is the mass creating the field. Okay, so our electric field is going to be exactly the same. One equation for electric field will be, instead of Fg, it'll be Fq. And instead of the m, it'll be the q. So there's a perfect alignment. So the electrostatic force divided by the charge, and exactly the same way, this is the charge brought into the field instead of the mass. And if you were to fill KQQ into R squared right into here, and one q would cancel, and so you'd be left with our second equation, which is KQ over R squared, where this q is the charge creating the field. So a perfect charge creating field. Perfect alignment with the magnetic, science 12-2. Perfect alignment with the gravitational field. So these are our 2 equations. The only difference is, in these ones, the direction. The direction is, for gravity, is always towards the center of the Earth. But the direction here could be towards or away from the particle, depending upon the nature of the charge. And so way back, many moons ago, we defined the direction of an electric field just so we could make sure everybody on the Earth does it the same. So for Thursday, you don't have to worry about direction, but I do want you to do a few of the questions. They'll all be with this first equation, and they're on page 646.